right, so one thing that I wanted to mention is we're going to have office hours today, but for the exam, which is on Monday, for you is 10:30 in the morning. You know that? I'm gonna have review sessions on transmission lines primarily. Start on Saturday from 2 to 4 and Sunday 2 to 4. Okay, just because we have not had enough practicing, I'm gonna go and do that. And then any other questions you may have, but I would like to do some review there. So I will send a note about that, but keep it in mind that this is gonna be, I thought it's better to do it a little later when you're gonna be studying for the class as opposed to do it too early. Any questions, concerns about that? Okay, so today we're gonna start with another interesting, very short example of how to match a real load to a transmission line. All right, other than what we did with the reactive element, which we did here using the Smith chart. There is another way of matching a real load to a transmission line, and we call that the quarter wave transformer. And that's what we are gonna do. And then after we finish that, we're gonna start on an example using Smith chart again. Okay, so I will draw here a transmission line. Okay, so a transmission line here. There, duplicate that. And I have a line connected to it, a source rather, connected to it. Like this. And this line has a characteristic impedance of 50 ohms and has a length. I can give it to you, the length usually on this line does not matter, but it has a given length. All right, then I have a load. I have a load that I wanna connect to this line. And this load is real. So I show it as ZL equals RL, or I just could have RL. And that is equal, say, 100 ohms. Okay? Now, the question is, how am I gonna do that without using a reactive element? There is a way, and that is called the quarter wave transformer. What is that? That is a quarter wavelength line which has a different characteristic impedance than my input line. So I show it like that because these two lines remind me that they do not have the same characteristic impedance, all right? And that is important. So visually, they give me this information and they're connected here. And that has Z0, and this one here has Z1. What I know is that now I want to connect this load. Okay, let me erase that. I want to connect this load to this line here. And then I want to find the length of this line, which is D, and its characteristic impedance. So the reflection coefficient right here, and therefore everywhere on this transmission line is 0. So now I'm gonna name the ports, the nodes rather, A prime. I will go here, B prime, and then I will call here C prime, all right? these nodes where the two lines connect. And I want to make gamma at C prime, which is, I'm looking now from the source side, all right? The source is behind me and I'm looking towards the load. So gamma at C prime, I'm gonna make it 0. If I make that 0 at this point here, then I know that it's gonna be 0 everywhere on the line. And what does that really mean? It means that all of the power that my source gives me is gonna go directly to my load, all right? Because there's not gonna be any reflected power. Okay. So let's try to do that. Problems like this, you do not solve it with a Smith chart, all right? Don't. You remember I told you that when we are matching a load to a source, you will never use a resistive element. A transmission line is okay because not a resistor. A good and a very good transmission line is not going to have losses that will be important to me. So I can enter a section of a line that I have to define, but I could not use a resistor, all right? We can only use either reactive elements or sections of lines, period. These are the tools that we have. And in this particular case, we don't even need to use the Smith chart. And I will show you, I will write in fact what happens under what conditions that test what we want. And then I will prove it to you. So in the quarter wave transformer, it implies this red line, which is the quarter wave transformer, has D equal to lambda over 4, first of all. That's why it's called quarter wave. And it has a characteristic impedance, Z1, which is the square root of my load, which is real. I will put it here so you remember it, RL, times Z0. Okay? So this is a quarter wave transformer. If you know your RL, if you know your load is only real, resistive, then you know D is always quarter of a wavelength. You know Z1 from here, and therefore you can make it. Now, this is called the quarter wave transformer. Here, let me write it also here. So you want quarter wave transformer. Okay, now I'm gonna prove it, all right? So let's assume we did not know these relations. And I wanted to find out both D and Z1. So how am I gonna do that? First of all, I would say to make gamma at CC prime, excuse me, to make gamma at CC prime equal to 0, we have to write gamma at CC prime explicitly. But to find the reflection coefficient there, we will need to find the input impedance here, all right? So Z input at CC prime. Now, how much is Z input at CC prime? Z input at CC prime is equal to Z1, I use the formula on the red line, all right? Is the input impedance to the red line. Is therefore ZL plus J Z1 tangent of beta D. And then I have Z1 plus J ZL tangent of beta D. Now, from the reflection coefficient here, to make it 0, what is the reflection coefficient at that point? It's gonna be Z input at CC prime minus Z0 over Z input at CC prime plus Z naught. All right? Okay. To make gamma CC prime equal to 0 from here, that implies that Z input at CC prime equals Z naught. All right? From the reflection coefficient. Okay, so now I want to make from, this is 1 and this is 2. So from 1 and 2, what do I find? I find here, first of all, I have to make Z input at CC prime Z naught. Therefore, I'm writing here Z naught. And then I have this expression. Okay, so this is a complex number. For an arbitrary value of D, that is going to have a real and an imaginary part. And therefore, we don't necessarily, all right, like this. So let's see how we can get rid of the reactive parts. Because if I keep the J components there, I know it's going to give me a complex number. And I cannot have, Z naught is real. I cannot have Z naught equal to a complex number. Okay, so what options give me that? One option is to make tangent beta D equal to 0, which means that I get rid of all of the J's. If I make tangent beta D equal to 0, however, so if tangent beta D becomes 0, what this equation gives me is that Z naught is going to be equal to ZL. But that is not possible because ZL is 100 ohms and Z naught is 50. So that is not possible, okay? You cannot have 50 equal to 100. No. So that is not possible here. Let me put not appropriate value. Okay, so what is another? How else, since I cannot have tangent beta D to be 0, what else can it be and get rid of the J's? It can be very, very, very large. If tangent beta D here becomes infinity almost, all right, becomes, I put that, then it's very, very large compared to its other term, which means that ZL is going to be very, very small compared to Z1 tangent beta D. And Z1 is going to be very, very small compared to ZL tangent beta D, no matter what values ZL and Z1 take, unless ZL becomes an open circuit. You cannot match an open circuit to 50 ohms, all right? So we're not looking at that. Okay, so now let me add one more page here. Okay, so it has to go. Add, okay, add page. Okay. Okay, there we go. You know, I'm moving the page and it doesn't want to move. How about that? That is weird. So, cut, copy, paste. Okay. All right, so now I can take 3 and that I can write 3 under these conditions. Therefore, Z naught is going to be equal Z1 And then I will ignore ZL in the numerator. So I will put J Z1 tangent beta D. And underneath it, I will ignore Z1 and it's J ZL tangent beta D. Beta D is very large, so, but it's equal, so I can get rid of this. And therefore from here, I get the Z naught is gonna be equal to Z1 square over ZL, which implies then that Z1 has to be equal to square root of Z naught ZL, where ZL is real, obviously. Z naught and ZL are both real. So for our, therefore, we found this expression, which I had given you, all right? So we found this, which is the condition for the impedance for a quarter wavelength transformer. Okay. Now, for our problem, it makes it Z1 to be, therefore, the square root of 50 times 100, which is the square root of 5,000. And that is going to be 50 times 100. It's 70.7. So this one gives me 70.7 ohms. So that tells me that if in this problem, I make D to be a quarter of a wavelength at whatever frequency we are, and the characteristic impedance to be 70.7 ohms, then I can match this 100 ohm load to a 50 ohm line. And therefore, whatever power goes from the source in the line, it all gets delivered to my load. Okay, that's a quarter wave transformer. And you're not going to have to prove any of this. You'll just have to remember these two expressions here, these ones, for a quarter wave transformer. These are the two things you need to remember. And as a matter of fact, I will put them here. So, okay. Now, any questions about this? Okay. We are gonna solve a problem now where we are gonna have a reactive load, like a load that has both real and imaginary part. And we are gonna try to match it using what we call a shunt element. Shunt means in parallel, connected like that. So I'm gonna write the problem. Example, that's another example. So example 1, or 2 rather, because that was example 1. Example 2. Next. Okay, example 1 was rather this one, the quarter wave transformer. Let me, because we did it as an example. Example 1. Okay. Example 2. Now I'm gonna give you this transmission line. Let me get a list so I don't have to do everything. I will take that and then eliminate some things. Copy, paste. All right, so I'm gonna erase that. Erase this. Erase that here. All right, so now I'm gonna extend this line And the problem that I have is this line is connected with a load okay, ZL. And this load is RL plus J omega L. All right, so now the load has a resistor and an inductor. So practically, instead of that, I could have shown something like this. All right, in terms of instead of a load. This one is RL. This here is RL plus J omega L. All right, so I'm giving that. And let's assume that I'm giving you now. Okay, so now I'm giving you in this that Z naught equals 50 ohms. I'm giving you that this one here has a length. And the length, we're going to use it just so we're not going to do anything specific with this, but we just want to know that we have enough length on the line, all right, to move, because we're going to do it with a Smith chart. Let's assume that here, this is 12 centimeters. Let's assume this is, so I'm setting up the problem here. Let's assume that we have a frequency of 10 gigahertz, that we have a Z naught on this line of 50 ohms, that R sub L, the resistor, is 100 ohms, and that the inductor is 1 nanohenry. All right? And now I'm saying I want you to solve it. So find a shunt react element, let me say element, to match the load to the line, to the source, if you like. Load to line. That's how we normally say it. And line is 50 ohms. What does shunt means? Shunt means in parallel. Okay, means in parallel. So you will see, we're not going to be able to finish all of this problem, but if we don't, we'll continue tomorrow. Okay, so let's see how we're going to do that. We have to, of course, somewhere on the line, place that element. So I'm going to take this line here and see what that really means. All right, you will always have to do that. So copy, I think it's going to copy the whole thing, paste. And I will have to erase that. Okay, what does that really mean? Is that I have to go somewhere on this line and cut a piece of the line like this, not a big piece, electrically speaking. It looks bigger than really is because of, you know, we have to be able to see it. But here, I will put an element in parallel, which means I'm gonna connect this like that and then put an element, which I don't know what it is yet. Okay, a couple of things. I know this element is reactive. Why is that? Because if I were to put a resistor in there, I will lose power. All right, so resistors are forbidden from using them for matching. All right, so we know it's gonna be reactive. Then we know it's parallel, okay? Now on the Smith chart, where we are going to have to use, you can only sum things. You cannot put one plus another. You cannot do multiplications. You cannot do divisions, which means if they are in series, all right, if you have two elements in series, like two impedances in series, on the Smith chart, you can add them. However, if you, this is Z1 and Z2. However, if you are in parallel, you cannot add Z1 and Z2. So what can you add in parallel only? Y1 and Y2. And what is Y1? It's an admittance. Okay, remember from circuits? The total impedance here, Z total, is gonna be Z1 plus Z2. And Y total here, Y total, is gonna be Y1 plus Y2. All right, so when you have to connect things in parallel or shunt, as they say, to put shunt elements, you will have to think of admittances. So you will have to use not impedances on the Smith chart, but admittances. So these are the things that you have to keep in mind. And therefore, this one here, which is an element I have to add, I will call it YS. All right. And that's going to be the element that I want to add here. All right. Now, if knowing that I can only sum admittances, then I will also need to think that when I go to the Smith chart, I will have to go as fast as I can on the Smith chart, because I don't have calculator, say, from impedances to admittances, and then do the rest. Okay, so the thing that are going to do to get on the Smith chart is the following. You have to normalize everything, all the impedances you have in terms of Z0. If you normalize everything, that your YS is gonna also the value coming out of the Smith chart. So everything that the Smith chart gives you is normalized. So that's what you have to keep in mind. If it gives you impedances, are normalized impedances, which means normalized with respect to characteristic impedance. If they are admittances, they are normalized admittances. What does it mean? Normalized with respect to what? To the characteristic admittance. What is the characteristic admittance? So characteristic admittance is nothing else but the inverse of the characteristic impedance. Okay? And therefore, a normalized admittance any normalized admittance, say I will call it YS, normalized, what is going to be? The real admittance divided by Y0. See? It's the same thing we do for characteristic impedances. And characteristic impedance here, so you remember, I'm going to post these things. Characteristic impedance is Z0, and normalized impedance is what? And if I had a ZS, normalized would have been ZS over Z0. And if you want to go to the Smith chart, you have to normalize And whatever the Smith chart gives you, exports to you, is normalized, okay? The length in lambda, the impedances in whatever characteristic impedance, if it's impedance, admittance is characteristic admittances, okay? So you don't forget that. So what is gonna be the next thing I have to do? I have an impedance, ZL. I know that Z sub L from here, Z sub L is, what did I say, R sub L? 100 plus J 2 pi F L. So I have to plug in here and I will say, let me start with what I have. All right, so that I put it here so you remember it. Do it like that. Okay, so you remember. So now I'm going back to my solution. Say, what do I have? I'll start with what I have. I have that ZL is 100. Then I have plus J 2 pi. I have that F is 10 gigahertz, 10 to the 10 hertz. And I have that L is 1 nanohenry, 10 to minus 9. And then this all is in ohms, therefore. So I have that this one is 100 plus J 20 pi. All right, in ohms, and 20 pi, here 20 times pi is 62.8, say 63 ohms. All right, so I have that this is 100 plus J 63 ohms. All right, to use the Smith chart, I have to normalize. Cannot go to a Smith chart, cannot even think about the Smith chart without normalizing. Normalizing this is 100 plus J 63 divided by 50. And that is going to give me 2 plus, how much is that? 63 divided by 50, 1.26. So that is my normalized impedance. That's what I have, and I will start with this. Okay, this does not work. All right, so let me do this again. All right, so now I'm gonna find it. How do we find it? We have to find the impedance of the circles. How many circles do we have? Okay, that's what happened here. So how many circles do we have on the Smith chart? We have 3. We have the resistance circles, which are these, the whole family, all right? We have the, we have then the circles for the reactants, and it's positive, are up here, negative down here. All right, and then what other circle do I have? Remember? Yes, and we have the transmission line circle, which has its center at the center of the Smith chart, and then depends, it connects with whatever load I have, and that is gonna be the third circle we can use. We cannot go to anything more than that. All right, so now we remembered it. We therefore try to erase them now that we remembered those. And I'm trying to find my impedance, 2. So I'm looking for a circle, the resistive circle that has gives all of the elements have value of 2, is this one. No, not this. Okay, fast. Okay, so it goes like that and goes through 2. Okay. And then I want to find 1.26. So I'm going out here to find 1.26. So this is 1.2, this is 1.4, this is 1.3. Therefore, 1.26, use green, is going to be here somewhere. And therefore, I'm writing this circle. All right, it's going to go there. And I find that they intersect at this point. And that's my impedance. Okay, normalized. So, in fact, to show you what I do when I solve problems using the Smith chart, I'm going to write this here, not on the lines. So I remember that this is my normalized load, L, excuse me, L normalized, which is 2 plus J 1.26. And now I do that, I remove the circles, don't need them anymore. And I have my load. Okay, so now practically on the Smith chart, I'm right here. That's where I am. And before I do anything, I know this is an impedance, but because I'm gonna add an admittance in parallel, I don't wanna work with impedances. I wanna transfer from impedance to admittance as fast as possible. How do we do that? We write the transmission line circle, okay? Which has a center here and goes through this, my load. So it's gonna be this circle. Okay, now, so let's, okay. So that is the circle. This is the transmission line circle. All right. That goes through my load. Then what do? I take a line that connects my, connects my load to the center, and I extend it until I find the other point on the diameter. That other point on the diameter is nothing else but my admittance. I will use a different color for the admittance. I will use this, all right? And I also write it out here so I know the value. And I say here, and that's how I do things so I don't get confused. This one is my normalized, in fact here. This one is the normalized load, but in an admittance form. And how much, I can even read it to see how much it is, if you want. If I ask you to do that, that's the resistive circle that goes through that. And if I look at the value here, this is 0.3 is here, 0.32, 0.34, 0.36, 0.38. So that value there is 0.38. And I write it 0.38. And then I'm gonna look at what circle goes through that point, and this is, let me see, this is 0.3, this is 0.2. So this is gonna be 0.22 approximately. But it's negative because it's in the lower hemisphere, 0.22. Now, if you had a calculator that does easily the inverse of a complex number, then you will find out that if you take your normalized ZL and you invert it, you're gonna find YL. But we did it using the Smith chart. Okay, so while I am on the transmission line circle, I'm looking at my circuit and see what I have done. So now I am here, I have change my ZL into YL. I have also normalized it, which means everything else is going to be eventually normalized. All right. And when I travel by, let me take that also, because if I do too many things here, copy. So go here for a second, paste. All right. So now I will erase this. And in fact, so you don't get confused, I will erase this one here. And I will leave only YS here. So when you need that, don't get confused. All right, so here, now I have changed ZL to YL. And now I know that I have to move by a distance, but not really. I don't know how much this distance is. And I have to move until I meet this YS. So if I assume that this is my A prime, this is B prime. Let's assume this is C prime, this point here, and this is the other end of the line is D prime, okay? So if this here, if at this point I see, let me also erase that one. If at this point I see an input admittance, because now I'm in admittance form, an input admittance at DD prime, all normalized, then practically from this point, if I am sitting here, looking this way, what I will see is the following circuit. I will see this one. Okay, copy. And then here, what is going to be in parallel to that YS is going to be this impedance Y in at DD prime, normalized, okay? And then if that's the case, what I'm going to see here at CC prime is going to be another normalized admittance at CC prime, which is going to be the sum of the two, YS plus Y in at D prime. All right, that's what I see. Okay, now I want to make Y for zero reflection here. I want to make Y input at CC prime normalized equal to 1. Or I want to make, as we discussed before, the Y input at CC prime equal to Y naught. If that happens, that the reflection coefficient is 0, because the reflection coefficient is, let me write it here, the reflection coefficient on the line is going to be, and then practically at CC prime, is going to be either Z input at CC prime minus Z naught, Z in terms of impedance is going to look like that. And in terms of admittances, it's going to look like this. Because the admittances are the inverse of impedances. Therefore, if Y naught is equal to my Y input at CC prime, then practically gamma at CC prime is going to be 0. That's what I want to make. So this is what I want to achieve. Okay. The interesting thing on all of this, and especially when I look at the Smith chart, I'm looking at the normalized. So I want my normalized CC prime to be equal to 1. Okay, after I add ys. So what does that say? That says that my y input, since ys is only reactive, my ydd input at dd prime is gonna also have the same real part with the y input at cc prime because of this relationship. Here, since ys is only reactive, has a j, all right, because we don't put resistances there. Then, and y input at cc prime is 1, normalized. That means that y input at dd prime has to have as a real part 1. So that says this one here. Okay, why is that important? When I am on the Smith chart here, this is my YL normalized. If I move, I will have to move until I stop. I will have to move by a distance d until I stop at the point d prime. So this point here is point B. I have to move along the line like this. I have to move until I find the circle, the resistive circle that has value of 1. Because if I stop there, I know that the normalized admittance at this point, because that is the circle that has a resistive part equal to normalized 1 is this one. All right. No, what did I do here? Okay, so let me. Okay. So if I stop here at this point, then I know that that admittance there, because now I'm working with admittances, that admittance there has real normalized part of 1. So I'm gonna stop there, and what the point that I am at is D, right here. This is the point here. All right, and we're gonna continue that tomorrow to finish it up. Any questions? I have recorded this and I'm gonna put it on Canvas.